Hello everyone and welcome all to this class. This is mathematics class and today we want to consider more examples under this topic we introduced in our previous video. We looked at this topic, the Rolle's theorem. So in our previous video we stated this Rolle's theorem and we can see the statement on the board. Suppose we have a function f which is continuous on a closed and bounded interval, and that function is differentiable on the open interval, and if the value of the function at the end points of the interval are equal, then you can find at least one point c which is inside the open interval such that the derivative of the function at that point c will give you 0. Now we solved one particular example and we showed that the function satisfies the hypothesis of the Rolle's theory. So we want to look at this function in this example too, and the function is f of x equals 1 minus x squared divided by 1 plus x squared. We want to show that this function will satisfy the hypothesis of the Rolle's theorem on this closed and bounded interval -1, 1. So let's start the solution to this problem. Now, the first thing you have to check whether this function is continuous on this given closed and bounded interval. That's the first criterion. The function must be continuous on the closed and bounded interval. So the question is this function continuous on the closed and bounded interval? The first thing you have to look at when a rational function is given to you, a function in fraction form. When a rational function is given to you, check whether the denominator of that function will be 0 at the given interval. Now, we have at the denominator we have 1 plus x squared. Looking at this closely, all the numbers from -1 to 1, if you substitute for x and do 1 plus the square of it, you will not get 0. We have checked the first thing that we need to check whenever we have a rational function. Now the next thing you have to check whether the whole of the rational function is continuous on this closed and bounded interval. Clearly the numerator we have is what? A polynomial, and the denominator we have is what? A polynomial. We said this in our previous class that polynomial functions are continuous everywhere on the real line. Since they are continuous everywhere on the real line, they must be continuous on that closed and bounded interval, which is just a subset of the entire real numbers. So let's make that statement. So what I just said earlier, I've already written it down. The numerator we have is a polynomial, and that's what I've written here, that 1 minus x squared, which is our numerator, is continuous on the given closed and bounded interval because it's a polynomial, right? And the denominator 1 plus x squared is also continuous on this given closed and bounded interval because it is what? A polynomial. Now, and the denominator, which is 1 plus x squared, is not 0 for any number you pick from -1 to 1. If you put it for x, replace it with this x squared, you cannot, and add it to 1, you cannot get 0. So this 1 plus x squared cannot be 0 on this closed and bounded interval -1, 1. So we are sure that the denominator cannot be 0. Now, whenever I have a rational function, the numerator is continuous, denominator is continuous, and the denominator is not 0, then the rational function must be what? Continuous. So that's what I've written down here. Now the next thing is we check differentiability, right? We check whether it's differentiable on the open interval. So let's differentiate the function f prime of x. I want to differentiate this. Which rule will we use to differentiate rational functions, we use what? Quotient rule. We use quotient rule. So for you to use quotient rule, you call the numerator u, call the denominator what? V. You now do v u prime. That is, you keep v, you keep the denominator and differentiate the numerator, right? Now if I differentiate if my u is the numerator, if you differentiate this numerator, differentiate 1, you get 0. Differentiate negative x squared, you get negative 2x, right? You are keeping v, which is the denominator. So our denominator is 1 plus x squared, then multiplying negative 2x minus, next one you put minus. This time around you differentiate, you keep your numerator and differentiate the denominator, right? Now if you differentiate the denominator, differentiate 1, you get 0. Differentiate positive x squared, you get positive 2x. So you have the derivative of v is positive 2x. Then what is your u? Your numerator, 1 minus x squared divided by v squared. This is the formula for quotient. This is the quotient rule for differentiation. You square the denominator. That is 1 plus x squared all squared. This is my denominator. Then I will square it. So if you simplify, let's expand this. Open this bracket. 1 multiply negative 2x is negative 2x. And x squared multiply negative 2x is negative 2x raised to power 3. We have minus here. Let's keep the minus. 1 multiply 2x, we have positive 2x. Negative x squared multiply positive 2x, we have negative 2x raised to power 3. All divided by 1 plus x squared all raised to power 2. So let's simplify further. We can open this bracket with the minus. We have 2x minus 2x raised to power 3, right? Now open this bracket with this negative. Negative of positive 2x, we have negative 2x. Negative of negative 2x raised to power 3, we have positive 2x raised to power 3. All divided by 1 plus x raised to power 2 all squared. Now something can cancel. Negative 2x raised to power 3 can cancel positive 2x raised to power 3. Then what you now have is negative 2x, negative 2x. Altogether it will give you negative 4x. You have negative 4x divided by the denominator, 1 plus x squared all squared. And this implies that f prime of x is equal to negative 4x divided by 1 plus x squared all squared. Now we are considering the open interval. The open interval is what? Negative 1, 1. I want this function, I want this derivative to exist. When we say exist, it means that this derivative should be a real number as you substitute the values of x in this open interval, numbers between negative 1 and 1. Negative 1 is not inclusive and 1 is not inclusive. You are checking the numbers within. As you replace x and put those numbers here, clearly what you will get will always be real numbers. Numerator is a polynomial, denominator is a polynomial, and of course the denominator cannot be 0 here. So I've written down what I've said. The function is differentiable on the open interval negative 1, 1 since the derivative exists on this open interval. So the next thing we are going to check, we will check whether we can find that point C, which is inside this open interval. That's a number between negative 1 and 1. such that the derivative of the function at that point will give us what? 0. We replace x with c here and solve and set it to be equal to what? 0. So we now say f prime at c. So you come to the derivative, replace x with anywhere you see x, replace it with c. So I have negative 4c divided by 1 plus c squared all squared. We will set it to be what? 0. F prime at c equals 0. We'll set it to be 0 and solve. And check whether that number c will be a number between negative 1 and 1. So let's solve. So in this one, you can easily multiply the both sides of this equation by denominator, right? So let's multiply both sides of this equation by this denominator. So if you multiply this place, multiply this quantity by this denominator, you can see this and this will get cancelled. You will now have negative 4c equal to multiply 0 by this quantity. If you use 0 to multiply any quantity, you get 0. Right? Now, you can divide both sides by what? The coefficient of c. This implies negative 4c divided by negative 4 is equal to 0 divided by negative 4. So I've divided both sides by this negative 4. So of course, negative 4 gets cancelled. You now have your c. Negative 4 divides 0, you get 0. Of course, 0 is a number between negative 1 and 1. Right? If you draw your real line, you have negative 1 here, 0 at the center, and 1 somewhere here. So 0 is at the middle. Is a number at the middle in this open interval. Okay, the function satisfies the hypothesis of the Rolle's theorem. So thank you so much for being part of this class. See you in our upcoming class.